Contractions of epithelial cell sheets in a tunicate. This is chapter 6 of the series. The chapter title is Modes, Plots, and Ridges. When I first described the external vascular system of a tunicate colony in chapter 1, the ampullae, the bulbs that form at the end of vessels, were considered the unit of contraction. The variables plotted and analyzed were projected areas of entire ampulla, and the focus was on regularity of contraction and the relation between different ampullae in one colony. It was only when I described contraction of a single surgically detached ampulla that the cell had to be considered the unit, since a single ampulla cannot contract uniformly. The volume must always remain constant, so some cells must be contracting while others are relaxing. In chapter 5, I described a model using a compromise between ampulla and single cells. Here the unit of contraction was proposed to be a ring of cells around the circumference of ampulla. The cells in a ring are likely to be coupled to each other more tightly than cells in adjacent rings, thus they could be considered a unit. A ring is also a pragmatic assumption for a unit, since ampullae are measured by scans perpendicular to the axis. Scan data is literally the diameter of rings. In this video, I will often refer to the rings as segments. A mode is a pattern, usually described by a simple equation, that represents a characteristic example of a process. Reality is usually a slight distortion of a mode, or a sum of modes. An example is the vibration of a violin string. The most prominent mode is a sine wave with the frequency of the fundamental. However, there are minor amounts of multiples of the fundamental that make a violin sound different than a harp or other instruments. The T, or traveling mode, is a sine wave of contraction which moves along the segments or rings of the ampulla. T plus modes move up segments of increasing indexes. The T plus 1 mode is one sine wave, T plus 2, two sine waves, etc. T minus modes move in the opposite direction, from segments with high to those with low indexes. Of course, the direction in which the segments are numbered is arbitrary. A single detached ampulla contracting in a T mode was described in chapter 2 as evidence for the cell being the unit of contraction. This flat contour map, made using Mathematica, describes a simulation of mode T1+. Colors indicate the width of segments, blue merging with green being small, and red merging with yellow being large. Pick a red band, the crest of a wave, and follow it up the ampulla segments 1 through 8. As you do this, time on the horizontal axis increases by 60 seconds, the period of oscillation of this ampulla. If you pick one segment, 3 for example, and follow it along the horizontal line of increasing time, the diameter of the ampulla changes as a sine wave with a period of 60 seconds. Results of the same simulation, but displayed using a 3D contour plot. In this view, we are looking straight down on the contour, so it looks somewhat similar to the previous plot. The same plot, but rotated so you can really see its 3D nature. This minus traveling wave moves from high to low segment index numbers. So as time increases, the crest moves down and to the right. Now a 3D view of the minus traveling wave. The stationary mode is very different. Waves don't move up or down ampulla, but cells in different segments or rings oscillate with different maximum amplitudes. In the S1 mode, cells at the ends and middle of the ampulla barely contract, while cells a quarter and 3/4 of the length along the ampulla contract and expand the most. In actual ampulla, the segment where the contractions are the least may not be in the middle, but may be off to the side. Along the top and bottom of this flat contour plot of the S1 mode are two series of alternating red and blue ellipses. The two sets are 180 degrees out of phase. If there is a red ellipse on top, there is a blue ellipse on the bottom, and vice versa, because the sum at each time has to be constant. In this 3D contour plot of the S1 mode, you see the red and blue wave crests fitting into each other to make a characteristic pattern. Remember this, we will see it later. A review of the steps needed to produce these plots of contractions. 1. Convert the video file to a set of individual images. 2. Use a plugin for the application NIH image to measure the width of the ampulla in each image. 3. Average over groups of 30 images corresponding to seconds. First, let's look at contractions of an ampulla attached to a colony. This is the colony described in Chapter 1 of the series. We will look at contractions of the 8 segments of the ampulla at the top of the colony, number 1. This is the type of plot used in our previous discussion of contraction modes. There are some complications in the first 300 seconds, but then we have simple sine-like contractions with vertical crests. Thus, all segments of the ampulla are in phase. These are the 6 ampullae described previously in chapters 2 and 5. They have been surgically detached from a colony and have no remaining vascular connection to the colony or each other. Most of the crests in this plot are orange-yellow, not red. It may be easier to follow the troughs, the green-blue bands. On the left, at the start of the video, for the first 200 seconds, the bands slope to the right as you go up the ampulla. It is contracting in the T- mode. After 200 seconds, however, the pattern changes. Now we see interdigitating crests, an S-mode characteristic. However, by 500 seconds, the mode is shifted again, now to the T+ mode, where the bands slope to their left as you go up the plot. This mode continues into the end at 1000 seconds. Now we see the same data, but in a 3D contour plot. The same plot as before, but I have drawn a rectangle around the region where the ridges of the lower and upper segments interdigitate. Next, the lower ampulla in the series, number 6. This plot of ampulla 6 shows a contraction pattern that is very stable throughout the 1,000 seconds of observation. It is clearly in an S mode. Here, looking at the same plot from a different angle, it's strange that segment 1 and end is where the greatest contraction appears to be. Now we look at contractions of a very large, long ampulla. It has a contraction at the middle and narrows at the lower end. Long ampullae are usually not uniform in width. We see that it is another ampulla that has a very stable contraction pattern throughout the 1,000 seconds. It is a hybrid of a T- on the bottom and an S mode above. If you are watching, it'll start out as an S, then it morphs into a T-. Now look at the effect of external compression on a contracting ampulla. At the start of this 1400-second video, the ampulla was contracting in S mode, with segment 1 oscillating the most and segments 4 to 7 moving out of phase with a smaller amplitude. The first compression occurs at 480 seconds. In 40 seconds, segment 1 became small and segments 3 to 5 became large. After that, there is no clear oscillation until the next compression at 990 seconds, which, after some time, induces faint hints of oscillation in segments 1 through 3. This ampulla was contracting in a T+ mode until the first compression at 480 seconds. Segments 1 and 2 briefly expand, but then there are no repeating contractions. However, the next compression at 990 seconds triggers a clear set of oscillations with a period like the original ones. There are many patterns of contraction observed in detached ampulla, but they can all be described as sums of two basic types: stationary and traveling. The stationary mode has one or more segments that contract and expand with other segments that move 180 degrees out of phase. Total volume is constant. A common simple case is two segments that contract 180 degrees out of phase. The phase of a traveling wave changes smoothly along the ampulla by 2n⁻, where n is an integer. It produces n-side waves. Ampulla can beat for more than 20 minutes with a constant mode, or they can change mode every few minutes. Compressing an ampulla with an external force typically suppresses oscillation for at least several periods, but it can also induce oscillations. Here we saw one case where compression induced modest oscillations, and in Chapter 3, a case in which compressing a dormant ampulla caused a dramatic burst of oscillation. This is the end of Chapter 6. It may be the end of the series. Uncertainty of future results is one of the characteristics of scientific research.